The graphs of logarithmic functions are also closely related to exponentials, of course, because of their calculational relationship. And in particular, we can highlight the inverse relationship on the graphs very easily. If you imagine a graph of 10 to the power x, and then imagine reflecting that through the line y equals x, then we get the graph of the inverse relationship, and we call that inverse function log sub 10, or log base 10 of x. So if you're not familiar with this, please do review the notes in your textbook about inverse functions and the graphing of inverse functions. But essentially it's the reflection. If we take this graph and reflect it across this line, we're going to go from the original function 10 to the x to its inverse log base 10 of x. There's a couple of features we want to capture here. Remember that 10 to the 0 is always going to equal 1, and so what we see reflected is that log base 10 of 1 is going to be 0. So these graphs always go through the points 1, 0. We also see an asymptote on this side here. Why? Because there's a horizontal asymptote in the exponential graph. There's going to be a vertical asymptote in its inverse. That leads us to some statements about domains. Well, the domain of log of x is x strictly greater than 0. Go back to our graph here for a moment. Only the positive values of x are where this log function here is defined. The range of log of x is actually all real numbers. And again, remembering the inverse of domain and range with inverse functions, if an exponential, we can put any number we want into an exponential, so its domain is infinite, and that means the range of its inverse has to be infinite as well. Just for reference here, we're going to sketch the graphs of the two other bases, e and 2. And just for the purposes of graphing, remember that the e is essentially 2.7, or for the purposes of this graph, we're going to get about as precise as unit digits, integer digits, so around 3-ish. So with that in mind, if we were to put some points on this graph, we would note that, let's do the 2 because it's the most straightforward. If we look at log base 2 of 1, that's going to equal 0. Why? Well, because 2 to the 0 is equal to 1. What exponent do we put in to get 1 with a base of 2? And likewise, log base 2 of 2 will be 1, and log base 2 of 4 would be 2. Again, thinking, what exponent do I need to base 2 to get 4? And so we can fill in some graph points here. We'd have that, and if we went out to 4, we'd have a number here, 2. Let's add the scale here. And it's also worth seeing that we could go to the smaller values. 1/2 would be -1. Why? Because 2 to the -1 is 1/2, and again, put the -1 in the exponent, and put the half as our response to the exponential. That lets us fill in another point here, a half, and we can see the pattern, a quarter, and so on. So this would be the graph of our log base 2 as a function of x. Now, what else can we do? Well, we were asked to do base e, which will have the same flavor, except with values around 3. So when it gets to about 2.7, that's when that graph is going to equal 1. Log base e of e is going to equal 1, and so we think that as being around 2.7. We still have the same property that log base e of 1 is going to be 0. Log base anything of 1 will equal 0. And on the other hand, 1 over e, or about 1/3, is where we're going to get the next point. So what we're going to see is essentially the same shape, but compressed vertically. In this case here is one way to imagine the relationship, log base e of x compared to log base 2 of x. And all the families of functions of logarithms have the same shape. Common point at 1, 0, and then an asymptote at x equals 0. They're only defined for positive x's, and then it's just a question of how quickly they grow once you get past the 0.10 and how quickly they approach the asymptote. If we look back to the 10 to the x, it grows very, very slowly and approaches the asymptote very, very quickly, but otherwise has the same basic characteristics.